Hello, friends. It's good to see you on our very last day. It's come to an end. Hard to believe, but thank you for sticking with me this whole time. Thank you for all of your efforts. We have evaluations to do today. Teresa, do you want to put yours in the envelope? Did you do that already?
Yeah, I put it in.
Okay, yeah, they're still sitting here. I didn't do anything. So we'll end 10 minutes earlier or so to do these. You all should have received an email from Qualtrics. Did you get that? Okay. So 1 point extra credit for answering some questions that give me actual useful feedback about your experience in this class. I can see which email addresses have completed a survey, but your email is not tied to your answers. So it is anonymous to the extent that 17 surveys are anonymous. So please feel like you can be as honest as possible. I really do want your feedback in planning what to do with this type of class and similar classes in the future. So since I know I'm going to run out of time, I'll just start by saying thank you. It's been a privilege to have all of you, and it's been a privilege to see you learn so much and grow so much. And if you ever have questions in the future, don't be a stranger. You have a license to email me and bother me. I will tell you that short, precise questions get answered more quickly than a book that's like, what do I do kinds of questions. But do feel free to make use of me as a resource. The only thing that I ask is that you pay it forward, because now you are going to know more about these models than other people that you know in your life, and they may ask you for help. And just like people were nice enough to answer my questions, and I'm nice enough to answer your questions, be nice enough to answer other people's questions too. That's all I ask. Deal? All right. Then to that end, can I answer questions about homework? Question 5 was fixed this morning. So that was a data glitch on my side, on the programming side, that I was able to fix because none of you were doing homework at 7 a.m. this morning when I sat down at my computer. So I was able to get in and do it. So are there any other answers that you cannot get or clarifications that I can provide? As of right now, I'm not planning on having any office hours next week unless some of you really want to come. And if that is the case, then I'll have to figure out when this room is open and when I can do so. But I think a lot of folks have already gotten a good start on this and may not need office hour time. I will be answering emails. I'm out of town the next 4 days, but after that I'll be back on Monday and available. No questions right now? Okay, well this is due the end of finals week. You've got another week or week and a half to do work on this. The Qualtrics survey, please complete that by the end of finals week as well, and then we'll turn in grades. Your current grades are updated, so I've re-downloaded all the databases and updated all the quiz scores, so you should know where you're at. I don't think anyone has anything to worry about last I checked. So long as you turn everything in, you're good to go. All right then. So this is a multivariate request week. We started talking about different types of multivariate, multi-level longitudinal models. The example that we were looking at was using SAS. So just to review the practice here, you can trick univariate multi-level software such as SAS Mixed into doing multivariate analyses by stacking multiple outcomes into the same column. So in the example that we're working with, I had 2 outcomes, response time to a number 3 match task and to a number 5 match task. This is example 9A. And I took those 2 columns, turned them into a single column called Y in a new data set. So SAS doesn't know that these are 2 different DVs. It's up to you to tell it that by using DV as a predictor. So in these models, things to remember, no int. If you take out the general intercept, then adding DV to every model term creates a DV-specific version of it. So for instance, in this empty model, y equals DV, I still call it empty because all that is doing is allowing a different fixed intercept for each of my outcomes. So there's still no predictors, there's still no time. Likewise, random DV, instead of random intercept, allows 2 different random intercepts. Their variances show up in the G matrix. and type equals UN ensures that there is a covariance between them. G-core converts that covariance to a correlation for you. Repeated DV then allows us to estimate two separate residual variances, one for each DV. Type equals UN here if you want them to be covaried. Since in this study people took both of these tests on the same day, a residual covariance makes sense, and that residual covariance at level 1 gets turned into a residual correlation via R-core here. So we looked at empty models for each. We looked at models with fixed slopes. This is a piecewise model for response time changes across 6 sessions. We then added random slopes to it and looked at examples of how to ask for DV differences in the fixed effects. So for instance, Model 3 here. Model 3 adds random slopes for each piecewise slope as well as for each DV. And then down here in the estimate statements, I'm asking it to contrast the fixed effects for each DV. So is there a greater rate of change in the first outcome than the second? Is there a difference in the rate of changes combined? So this is a 2-degree freedom test across outcomes and so forth. And we get the answers to all of that. I have tried to label everything as much as I could here so that you'll know what you're looking at. But the benefit of setting it up this way, the solution for fixed effects gives you the significance test for each fixed effect for each DV. The type 3 tests of fixed effects down here then gives you an overall test for each predictor across DVs, what's known as a multivariate test or an omnibus test. And then estimates provides the difference in the fixed effects. So the intercept for number match 5 is significantly higher. The first slope for number match 5 is not different than that for number match 3. The second slope for number match 5 is less negative than for number match 3. So to know what these numbers mean, you have to refer back to their fixed effects here. So for instance, this last comparison, there's a significantly negative slope for number match 3, a non-significantly negative slope for number match 5, and the difference between those two numbers is right here. So that positive difference means that the second DV is less negative than the first. So you got to have all 3 pieces of information to put it together. And I think this is where we left off. So any questions on the setup, the logic, the code? So again, why would you do a model like this? 2 reasons. Number 1, you look at correlations among intercepts and among slopes and among residuals across outcomes. Or number 2, you want to test differences in the effects of your predictors across outcomes. So Katie, do you know what you're going to do now? You got it? All right, I made this just for you, copy paste. It's like Make-A-Wish week here. I've got structured residuals coming up too, because a couple of you have asked me about that. Make-A-Wish. So here's one last example. I'm throwing age as a time invariant level 2 predictor of everything. So I'm picking up 6 new fixed effects of age, 1 for each intercept, 1 for each first slope, 1 for each second slope. Here's an example of how I would test the differences in the effects of age on each of my predictors. So does age affect the intercept differently? That's the first one here. Does age affect the first slope differently across DVs? Does age affect the second slope differently across DVs? And does age matter on the whole? For the first outcome, that's this first contrast. For the second outcome, and then are there DV differences in the overall effect of age? That's the third one here. So then you end up with output that is fairly straightforward. Here's all of my age effects per DV. It looks like there are age effects on the 2 intercepts, but not on the slopes. And if I come down here, DV difference in the main effective age on the intercept is not significant. So these 2 effects on the intercept are statistically equivalent, according to this model. And here's some pseudo R-squares for everything. And I did put up the new version of the macros that has a pseudo R-square for multivariate models. There's some extra steps that needed to make sure that you get separate output for each DV. And also I modified the one for, to total R-square. That was the other one. That one has a new one. I had to modify the pseudo R-square one, but it's the same code otherwise. And here's total R-square for each of the two from the combination of time and age. And here's some words that describes everything. So how I would talk about all of this. All right. Any questions on that? Okay. I'm shutting this one down then. And I want to ask you, which one do you want to do next? I've got a multi-level path model for fluctuation type data, or I've got a growth model that has level 1, level 2 relationships and eventually ends up with structured residuals. Which one do you want to do first? Fluctuation one? Sure. So here's why I'm building this. Some new slides here that are likely to piss some people off, but oh well, I have tenure. So here's what not to do. So this is picking up on slide 33 here. Using structural equation modeling for longitudinal data is better than using path modeling, even when you don't have very many occasions for these reasons here. So let me show you two types of models that I want you to never, ever do. Here's this one. There's an article that was recently published that I gave you to read about it. This is my version of it, a model that needs to die. The autoregressive cross-lag model, this thing is ubiquitous. It's 17 kinds of wrong. So this idea that you need to control for the previous occasion, when people tell you that, what they're really trying to say is, well, you need to control for between-person differences. But by putting these autoregressive paths between the variables here, what they're actually fitting is an AR1 covariance structure model. They're saying that the variance of each variable stays the same across time, and the covariance is an exponentially declining function of the distance in time. So those paths can only be constrained equal if these are equal interval assessments. But more to the point, this model does not assume that you have a random intercept or a random slope. It assumes that all of the variance and covariance can be described by an AR1 structure. I have never once seen a longitudinal data set that held true for. AR1 typically sucks. That is the taper genes model. Do you remember that one? It gets too narrow at the bottom. It predicts that the covariance declines too quickly across occasions. And so then in looking at these cross paths here, when you see only one path in longitudinal data, what kind of path is it, folks? It's my favorite word that I made up. Well, I made up the meaning for it, I guess. Smushed. These are smushed, folks. The reason people do these models is to try and see which came first, right? Which is the driver and which is the result. But this model completely misrepresents the difference between between-person variation and within-person variation and smushes it all into one cross parameter here. Another problem that I have with it that not a lot of other people do, but I'll just tell you my perspective, it bothers me that the residuals at the same occasion are correlated. That's what this two-headed arrow conveys. Whereas you're looking at direct relationships across occasions that are adjacent. To me, if you want to say that, okay, so I don't like this for two reasons. I don't like the smushing, and I don't like the lack of contemporaneous. The former is definitely a problem. The latter is an opinion, so you can decide if you agree with that or not. I'm going to show you how to do this the right way. And also, don't do this either. Take this one with it. Sorry, Scott Maxwell. He's a very nice, very smart man, but I hate this freaking model. Same problem. These are all smushed. So this is a longitudinal mediation model in the sense that it takes time for X to go to M to go to Y. And that's what his whole article is about, is that mediation logically takes time. And so if you're looking at mediation cross-sectionally, it's not a good approximation for what you would see longitudinally. Totally agree. The problem is that all these paths are smushed. So I want to show you how to do this the right way also. So this we'll do first then by popular demand. This is the path model one, the 9B. So this is using the same data that came from Chapter 8. I revised this example quite a bit from the last time I gave it so that it's a little bit more straightforward and potentially helpful. But this is making use of M+ software. So I'll show you the first model, because the first model is univariate. It can be done in SAS and M+, and from there it's only going to be M+, because there is no analog using SAS proc mixed, the same exact specification. So here's the story. When you're grumpy, you feel crappy. When you're stressed out, you feel crappy. Is the reason that stress makes you feel crappy because stress makes you grumpy, which makes you feel crappy? That's my mediation model. So I have daily stressors, daily negative mood, and daily physical symptoms. Stressors is a binary variable, whether or not a stressor was experienced on a given day. Because this is binary, I cannot bring it into the likelihood in M+ unless it is an actual outcome. So I'm leaving this as a box, meaning I'm treating it as an observed predictor. I then put in the person mean of that variable centered at 40% so that it will serve as a contextual effect. Physical symptoms is my Y outcome here, and the circles are meant to convey their different piles of variance at each level. So on the top, the between-person model, this is random intercept variance in physical symptoms. Here's tau squared U 0 Y. And then here's level 1, residual variance in physical symptoms at the within-person model. Likewise, negative mood is decomposed by the model into its variances. So because negative mood is both an outcome of stressors and a predictor of symptoms, that's why SAS can't do this model in mixed, or Stata, or SPSS, or any other mixed package that's univariate. It doesn't know how to make both of them, it doesn't know how to make a predictor be both a predictor and an outcome in a multi-level analysis. So there was a paper I saw, I think Dan Bauer and some friends, that took out all the between-person part of the model. They detrended each variable for the person mean, and then they tricked ProcMix into doing the bottom part. But that misses half the story. So I want to show you how to get the full story of mediation, but it requires two different levels of analysis, between-person mediation and within-person mediation. And in this example, time is not relevant. It's a fluctuation study, so I don't have random slopes for time that I'm worrying about. In the next example, I will. Okay, so I have notes on here about what happens when you treat things as predictors versus outcomes. When you treat these variables as predictors, these stressor boxes, it's just like it is in ProcMixed. Stress is not part of the likelihood. You can estimate fixed effects for stress, but its mean variance and covariance are not parameters that are being found, so you cannot have any missingness on stress. Each row still has to be complete, and this is using stack data the same as in SAS. Negative mood and physical symptoms, though, are outcomes. Their model parameters are getting found as part of the maximum likelihood process, as well as their means, variances, and covariances. So you can have missingness on those. So each row has to have at least one outcome to be included, but it doesn't have to have both. Now that flexibility comes with a price. There are distributional assumptions put on both of those now because they're model-based. So in this case, we're assuming multivariate normality of the random intercepts with each other as well as with the residuals with each other. Okay. Questions on the story, the setup? All right, so welcome to SAS versus M+. So here's my first model. I'm looking at just the relationship of stress predicting symptoms before controlling for negative mood. So in mediation literature, this would be called the C path, but it's just this bottom one right here, leaving negative mood completely out of the model. Consequently, this is the time-varying predictors approach known as grand mean centering or constant-based centering, and I can fit this model in SAS. So I have women, age, and their interaction as a predictor of the intercept as controls. That was developed in this example for Chapter 7. And I'm adding level 1 stressor, which is the 0, 1 variable, and person mean stressor centered at 0.4. So this model then, because of these two variables, is going to give me the within effect for stressors. Using grand mean centering at level 1 means the level 2 effect is the contextual effect. It's the extra effect of having a person who has a lot of stressor days after controlling for whether or not today is a stressor day. After controlling for level 1 is the definition of a contextual effect. And to get to what the total level 2 between effect is, you would add the within effect to the contextual effect as shown by this estimate statement. And so the SAS output then that you're used to seeing is on the back here. There is not a significant level 1 effect of stress, so whether or not you report a stressor on a given day does not predict your symptoms that day, but there is a significant contextual effect such that after controlling for whether or not today has a stressor, for every unit more person mean stressors, so this is a change of 1, symptoms goes up by 1.3. So given that this is, if I want to talk about 10%, I move the decimal like that, and I would say that there is a 0.1% in symptoms, 0.1 point increase in symptoms per 10% increase in stressor days. So that's old hats. If I add this within effect and this contextual effect together, I get the full between effect, which is the effect of person mean stressors not controlling for what you have today. So I know I'm going kind of fast because this is stuff that we've done before. Are there any questions about the SAS version? All right, now welcome to M+, folks. Dun, dun, dun. I have a love-hate relationship with M+. It can do everything, but it sometimes doesn't do things for no apparent reason, and it sometimes messes with stuff for no apparent reason. And this week, in building these examples and then the stuff that I'm doing at Oklahoma State, I have discovered new ways that it is screwing things up without me knowing. So I'm thinking I need to write like a Teacher's Corner article or something, because if I can't figure this shit out, what chance do students have? So take that as it may. It's also expensive, so there's that. So in M+, the headers here are colored blue. There are sections that you would have that identify your data, and it tells it all about your variables. So in M+, the only kind of data file you can use are text-based files. So .dat or .csv, it will take comma-separated values, or the CSV files. I tend to make those because if you want to check that your data is right, you can double-click on it, and most of the time it will default to open in a spreadsheet where it looks like data. I just find that easier to work with than a straight text file. So you have to convert your data set into a comma-separated values file before you can use it in M+. In the piles of variance materials that I pointed out last time, there's code in each of the 3 programs that I tend to work in on how to do that. So it's just an export statement. You can import different types of data. These are the defaults, that it's free format and that it's individual level data. Names. This is so important, folks. About, I'd say 60% of the time when someone comes to me with a badly fitting model, it's because M+ did not read the data correctly. Seriously. It is so common. You have to write the name of every variable that's in your CSV file in the order in which it appears. Now that sounds like that should be trivial, right? But if you're working with very large data sets, or you make new variables and they get appended to the end, you can forget the order in which these are listed. So in the SAS code that goes with this, I have examples of how to make sure that your data set is correct. Cut your data down to just what you need to go into M+. Get rid of any string variables, get rid of any dates. It does not read those very well. And at the very beginning of the output, you will get a set of descriptive statistics, means, variances, ranges, and that kind of thing. Check those to make sure they seem plausible before you go any further. The other catch is that each of these names, everywhere in the program, can only be 8 characters or less. Welcome back to 1985. We missed you. That's what kills me about this program. It's like the data sets and the syntax are 1985, the models are 2018. There's an imbalance there. You can tell where they put their efforts in. So you may have to rename some of the variables so that they fit this convention. M+ doesn't know what they used to be called. The CSV file you're importing does not have a row of names at the top. That's another thing people screw up. It doesn't know what the columns are to be called. So you'll see, for instance, what was PM stress 40 in SAS, I cut down so that it had fewer characters. So you just have to keep track of what things are called here. After names, use variables indicates the model, the variables that are to be included in the model. If you forget this line, it thinks that every single variable that is in your data set is going in the model, and that can cause big problems. So don't forget that. Likewise, you need to tell it what kind of missing data you have. Technically, it accepts dots or blanks, but I have had terrible luck with that. I am superstitious. I always make my missing data a number, usually a negative number. That's not possible. So that's part of the code that I put there, is to create an array statement that does that. These commands here are specific to multi-level models. Cluster is how you tell it what your level 2 nesting variable is. It is the analog to subject on the random line. Within and between is where you list predictors that are to be placed only at one level or the other. So in this model, level 1 stress is an observed variable. I want it only at level 1. It will go here. Person mean stress centered at point 4 is only level 2. It goes here on between. And likewise, my level 2 time invariant covariates are on between age 80 in women. There is no defining interaction terms via asterisks in the model in M+. So any interaction terms between observed variables, you have to physically make into a new variable. So whereas I had in SAS, I had the variable women by age 80 as the interaction term, I had to compute that here. So I have another variable called age sex that I had to manually create with this define statement that is the interaction term. Any new created variables that you use and define have to go at the end of your use variable statement, or it will yell at you. So there's all these conventions that you have to learn to use this. Type equals 2-level random creates the type of syntax that we want. Estimator is ML. It does not have REML, but there's also MLR, which is a correction for non-normality. To keep the results the same across programs, I'm not using that. Okay. Questions on that part? Now the fun part. Fun with the special characters row on your keyboard. So percent sign within percent sign. Percent sign between percent sign. Those are model commands that are used to differentiate which terms are included at what level of the model. In 2-level models, it's within and between. In 3-level models, there's 2 kinds of between, each of which is separated by an ID variable. So I have examples of 3-level models. If you ever need to fit them, I'd be happy to send you those. In terms of the code, I've tried to indicate what each thing does, but we have, you'll note, symptoms listed in the within model as well as in the between model. So that's my outcome that is being partitioned into variance that is between persons in the intercept and within persons in the residual. So when I have symptoms here on the within part, what I'm actually referring to is its residual variance at level 1. I don't technically have to type that, but when it comes to M+, I hate trying to memorize what defaults are, and so I tend to list every model parameter so that I know what all is there for my own sanity. So I am estimating a residual variance for symptoms. Likewise, the word symptoms all by itself on between is referring then to its random intercept variance at level 2 instead. The only way that you would know that is this within versus between distinction. More generally, when you list a variable, you are referring to its variance, whether it is leftover variance because it's being predicted or just its variance to begin with. M+ knows based on the context of the model. Symptoms has a fixed intercept. Things in brackets refer to intercepts and means. An intercept is used for a variable that is being predicted. A mean is used for a variable that is not being predicted. These parts right here are regressions. It's y on x. So think of on as an equal sign, like that, and it will make more sense. Y equals the model. So it's y on x. The terms in parentheses are labels. I am using labels so that I can actually create estimate statements down below. So this is the main effect of women predicting the intercept for symptoms, main effect of age predicting the intercept for symptoms, the interaction of age by sex predicting the intercept for symptoms, and the main effect of person mean stressors predicting symptoms, which is going to give me my level 2 contextual effect. Okay. With me so far? All right, now here comes the funky part. This is the part that I need to write the teacher's corner about. That thing. It is analogous to the use of beta as a level 1 placeholder in a 2-level model. So I am creating a name for a new term. My name that I've created is on the left here of the bar. WPX to Y means I'm calling this the within person effect of X predicting Y. So X to Y to me goes with this picture here, within person X to Y. That path, I am naming this. What that path is then defined after the bar. It is the regression of symptoms on level 1 stress. So just like we would put stress in as a level 1 predictor with a beta 1, within person X to Y is like the beta 1. It's just a name. Then at level 2, just like we would say beta 1 equals at level 2, the fixed and random effects are then referred to at level 2. So in brackets is its fixed effect, because intercepts and means are referred to in brackets. The mean of this new variable is its fixed effect. Listing its name would refer to its variance. So beta 1 essentially can have a mean, which is the fixed effect, and a variance around it, which you know of as random slope variance. In this model, however, previous analyses said that it didn't need to be random, so this at 0 shuts it off. That is necessary. By default, everything is random. Everything. So I have a fixed level 1 effect. That's going to be the within person effects, and it shows up right here. I have labeled it that. Last but not least, model constraint is the analog to estimate statements in SAS. It's used to create linear combinations of estimated parameters. One thing that's nice about it, though, is that it's not restricted just to fixed effects like estimate is. You can actually make linear combinations of variance components. It works by declaring a name for whatever new term you're going to make it create. So here I'm creating a new term called BPX2Y, which is I want the between person effect of x to y. So in the same way that over here in SAS, I said the between person effect is the within person plus the contextual effect at level 2. Right here, I have the within person, which is the label that goes with the fixed effect of the level 1 predictor. And here's the contextual effect, which is the label that I wrote that goes with the level 2 predictor. These also can only be 8 characters, so it gets a little tricky to try and come up with unique combinations. Okay. How are we doing? So this gives us the exact same model as in SAS. In multi-level models in M+, if you don't have a covariance matrix to come back to as the answer key, you don't have model fit. So when you invoke random slopes, which is what you've done in using this placeholder syntax, that automatically kills any absolute model fit statistics. So you don't have to worry about absolute fit, the same as in MLM. The parameters are listed in an order that it likes, not the order in which you wrote them. Because why would you do that? So within level, residual variance, here's symptoms. That number, 0.6, is right here in SAS. So within level residual variance and symptoms is my level 1 residual variance. Analogously, residual variance and symptoms down here in the between section is my random intercept variance, which shows up right there. So this language can be confusing because the term residual variance shows up both places. What it means by residual is predicted, left over. I would call it leftover random intercept variance. It calls it residual level 2 variance. Then we get to our ons, which are always listed first after any buys. And those correspond to our fixed effects here. So here's those 3 and that one correspond to the 4 lines of on. So the contextual effect is the 1.33 here. It shows up for person mean stressor 40. The fixed intercept for symptoms is down here under intercepts. So that's the 1.5 right here. And now this thing. The mean of WP x to y. That's M+ code for, that is the fixed effect of our level 1 stressor predictor. It's mean because it's not being predicted by anything. So it's like the mean of beta 1, you can think of it that way, although there's no random variance around it, which is why variances for WP x to y goes to 0. This 999 just means that it's a fixed parameter that wasn't estimated. So I told it, do not give me a random slope variance, please. And it said, okay. And it gave me a standard error of 0 with an estimate of 0. Last but not least, here's my between person effect of stress that I created as a new parameter, and that matches what I got out of the estimate statement over yonder. Okay. How are we doing? Now, is this convoluted or what? Why the hell would I ever do this on purpose? 2 reasons. We're switching from this to this. This is the idea of a truly multivariate model using observed predictors for the x side, switching it to be random effects and residual variances instead. The other reason I would do this is whenever you're in a situation where your predictor has random slope variance 2, which is the next example, then we have to do it this way. So at this point, to fit a multivariate model between M and Y, where both are being treated as model outcomes, we have to switch to M+. So I have the analog in SAS using observed variables, and I have the results here. It's not the same model, though. What SAS is doing is this version with the boxes. What M+ is doing is this version with the circles. So the difference is whether I carve up the variance in person and mood or whether I let the model do it. So in SAS, I carved it up. Here's time varying mood centered at 2 and person mean mood centered at 2 so that we get within and contextual effects the same as in M+, and I get the between effect the same here. So this is the reason to learn this new package and to be able to do this is to be able to do, this is a multivariate multi-level model with directed relationships between X and Y. So everything is the same here, except there's no references to mood on within or between. If you say that a variable is getting used in the model, but you don't put it on within or between, it thinks it goes on both levels, and it's going to try to find its variance at both levels. That's what we want. Note that mood is still centered at 2 because the same logic of centering predictors still applies. We want the intercept to be meaningful, so I centered it so that 0 meant 2, which is meaningful within this scale. So the syntax looks remarkably similar with a couple of switches. Mood 2 now gets a residual variance also, the same as symptoms does at level 1. I still have my beta 1 placeholder here for the relationship of mood predicting symptoms at level 1. At level 2, symptoms gets a fixed intercept, so does mood. Symptoms gets a random intercept variance, so does mood. And here's the fixed effect of mood predicting symptoms at level 1. Here is its random variance, shut off. Here is the contextual effect of level 2 mood predicting symptoms. And here's how I get the between effect, the same as in the previous model. So why am I fitting this model? Not just multivariate, but why do it at all? In the logic of mediation, most of the time people, what they want to know is whether or not this bottom path changes after you control for negative mood, but I want to know the opposite too. I want to know if negative mood predicts symptoms before I control for stressors. Because if this path over here isn't significant in the full model, I don't know if it was never going to be significant or if it's not significant anymore after controlling for stressors. If I want to differentiate those two types of outcomes, I have to know what is the path from stressors to symptoms without mood. That's what we just did. But now I'm doing the analogous. What is the path from mood to symptoms without stressors? And here it is. Let me find it. Let's scroll too far. M to Y. So I've got two sets of output on here because I want to show you what happens when you set up the model one way versus another. So the new terms that are not being estimated in SAS are the means and variances of the mood variable that is now considered an outcome even though it's a predictor. So here's the residual variance for mood at level 1. Here is the fixed intercept for mood at level 2, which is in the means column because nothing is predicting mood in this model. And here's the random intercept variance for mood. So those three terms are the things that are being predicted uniquely. Here's my contextual effective mood at level 2. Here's my level 1 fixed effective mood at level 1. There's the random slope variance for the level 1 effective mood that I shut off, and here's my between. So this model is exactly the same as before, just using mood as a model-derived outcome. It made the piles. No person mean centering required. Okay. Questions? All right. So let me show you then what happens if you set up the model a different way. This is going to be statistically the exact same model. It has the same parameters in it. However, what they mean is going to change. So instead of using a beta 1 placeholder thing, an alternative that you will see in their examples is to put an on directly in the within model. So instead of this within person M to Y label and a bar in front of it, you just write that part directly. You can do it this way whenever you want to have only a fixed effect at level 1 with no cross-level interactions, which is what it is in this current model. However, when you set it up this way, at level 2, you get a between effect instead of a contextual. Just 'cause. So I have the between label here, and I'm asking for the contextual via model constraint so that you can see what happens. So then the terms then in bold highlight the differences in the output. So if you don't use the beta 1 placeholder syntax, you get the regression at level 1 directly within the within model. You don't get anything about that term and the level 2 model. You get the between effect instead of the contextual effect, such that the linear combination down here gives the between and this one gives the contextual. And you know how I figured this out? I made up the data, so I knew what should have happened. So here's the full mediation model, then, putting both of those together, both of the previous models being estimated at the same time. So this is why I have the labels as they are, using mediation language. This is X to M, X to Y, M to Y, corresponding with your typical mediation labels. Only symptoms and mood have residual variances because they're the outcomes in the model. Likewise, I've got all three fixed and random effects at for the level 1 and the level 2. Excuse me, these are level 1 fixed effects, level 2 random variance for each are all shut off. And here are the level 2 paths, which are all contextual effects, which means then that I had to make first between person effects within plus contextual, and then the indirect effects. So these are the things, too, that make M+ useful. You get a direct estimate of the indirect effect, which is the test of mediation. So if that multiplicative term of the two paths together is significant, you can say that the relationship between X and Y is different before versus after controlling for the mediator. So I have a within-person indirect effect. I have the contextual indirect effect that's directly from the model parameters, and I have the between-person indirect effect that is a linear combination of those two things. And here it is. So I have a significant between-person indirect effect. So part of the reason why people who have more stressors feel crappier is because they also feel grumpier. But that relationship doesn't appear to hold after controlling for the level 1 variables because the contextual indirect effect is not significant. And the within-person effect for the indirect effect is not significant. So there's no mediation at level 1 across days. There does appear to be mediation at level 2 to at least some extent. And so this is why We can't do this kind of thing or that kind of thing, because level 2 and level 1 are not the same. This syntax is somewhat more convoluted because I'm trying to add interactions with sex to predict these things as well. So this demonstrates how to make an interaction of an observed variable with a latent variable, which becomes a latent variable interaction. So not too many of those that you can estimate at the same time, but that's an example of how to do it. And here's some words. It says everything that I just said. Ta-da! So if you report these p-values on your output for the indirect effects, someone is going to yell at you. You're not supposed to do that. You have to correct them somehow for potential non-normality of the asymptotic sampling distribution of the indirect effect. You can't do bootstrapping in M+, but you can bootstrap the estimates. So that's what I would tell you to do. In practice, I have never seen this matter, ever. But some reviewer is going to yell at you for it. You should probably do it the right way. I can't imagine it would change these results to do any different kind of p-value. But just to say that bootstrapping that you can do for single-level models in M+ is not available for multi-level models as of right now. Okay. Questions? All right. Then I'm shutting this one down, and in the brief time that we have left, let's talk multivariate change. So this is Chapter 9 data. I have monitoring measured across ages 12 to 18 and risky behavior. So these are spaghetti plots showing how each relates to age as well as how each relates to each other. I made up these data. I know what the right answer is supposed to be, and that helped me actually figure out what M+ was trying to do. So if I just want to know how the intercepts and slopes for risky behavior and monitoring are related to each other, here's my multivariate model I can set up in SAS. Here's the same sort of dummy code switches mechanism that I taught you before, and the output is very straightforward. If I want to do this in M+, this is what the code would look like in the two-level models. So you'll note that I have beta placeholders here for the age effects, as well as this one is just allowing a covariance. These are all covariances at level 2, and this is getting me the same thing as G-core down here. So SAS and M+ are doing the same thing. But if I want to have monitoring predict risky behavior, then I can only do that in M+. So it's the same situation as before, where I want both of my variables to be outcomes. Each one needs to have a random slope for age in it. So I'm setting up my random slopes here. I'm setting up a placeholder for the level 1 effect. I'm setting up my level 2 regressions. And I want to point out what you get by default here. Intercept to intercept relations are contextual, slope to slope relations are contextual, but mixtures of the two are between, for reasons I have no idea why. So here's how you get the missing pieces. M+ gave me an error message saying that I had confused it, but this model should be acceptable. Here is doing the same thing without the placeholder syntax to show that for whatever reason, one of the effects is still contextual and the others all switched to between. And I was like, what the hell? Why is that happening? I don't know. So here's how I figured that out. If you switch it to just a with instead of an on, then everything you get at level 2 is between. So here is the structured residual stuff, folks. This is how to estimate the same model as a structural equation model. It takes a wide data structure where each variable at each occasion is one outcome. So there's a data long to wide option that I use to flip it from stacked back into multivariate. Here is my latent growth curve model, my bivariate latent growth curve model, Andrew. That's what this is. If you have the level 1 effect, which is right here, as a regression, then the same thing happens, that the intercept and slope relationships are contextual where the others are between. So the switch to fixing that is to do structured residuals. So here we go. In the few minutes I have left, let me explain this effing thing to you. So this is a term that was invented by, I think, Patrick Curran and his friends to describe how to trick M+ into making it so that everything at level 2 is between. That's what we're doing here. There's no phantom variables, there's no anything. It's just a programming trick. All we're doing is taking each residual variance and we are renaming it. So M+ thinks that I'm defining a latent variable for each residual variance that is perfectly indicated by the observed version. So I put an F at the front of each of these to say that these are now factors. I did that for all the riskies and all the monitorings. You then have to shut off those factor means because residuals don't have means other than 0. You shut off the old residual variances, and now we estimate them for the new ones with the F in front, and I'm holding them equal to each other as I did in the previous growth model. P-width means pairwise width, so this is estimating the contemporaneous effects as covariances. So it's analogous to this curved path here, except this is now right because I've gotten rid of all of the BP smushing and estimated it as part of the model. And here, then, are your cross-lagged effects. So this is monitoring at one occasion, predicting risky at the next. This is risky at one occasion, predicting monitoring at the next, where PON means pairwise on. So 12 to 13, 13 to 14, 15 to 16, and so forth. So this is the right way to do a model like this, where you have separated out intercept variance, slope variance in each of the two variables, and these paths are only amongst the level 1 residuals where they belong. In addition, you get to have paths between the intercepts and between the slopes, and in the instances of this model that I have seen, most of the time they fix those, they estimate them as covariances, so that the level 2 model is agnostic as to which came first. So rather than having regressions between the intercepts and slopes, they estimate covariances. The only regressions are that part of the model, the cross-lag. And since I made up these data, I can tell you what happened. That's a type 1 error right there. In these data in the population model, there was only a residual relationship at the same occasion. So that isn't right. This one's right, it looks like. And the covariances between residuals at the same occasion are significant, as they should have been given the population model. So that lends some support to my initial opinion that one should not estimate lagged relationships unless you control for contemporaneous. I just had a paper I helped publish in Child Development where I had to fight tooth and nail with reviewers about this point because they all wanted me to do this model, and I didn't want to do this model. I wanted to control for contemporaneous, which meant two different models, switching which came first and looking at various indices to see which one seemed more believable. So yeah, no words for this one because I ran out of gas by the end of this, but all of the words are in Chapter 9 for these data, so you can borrow those words. Ta-da! So, questions? That was a lot, wasn't it? Well, hopefully, at the very least, these can be examples for you to draw from in the future if you need to use these models. It's not a question as to whether MLM or SEM is better. It's a question as to which is less annoying to set up the model you want. Ultimately, that's the difference. And I'm hoping that some of these idiosyncrasies go away in later versions of software, and that if I bring this class back 2 years from now, but we will see. So, All right, then if that is it, I'm so sad. I'm not going to see you guys anymore. Some of you I won't see like ever, probably, because you already had my other class. But if you haven't, please come back in the fall. Now we get to do evaluations. So let me, can I have a volunteer to take these across the hall to Suzanne? Erin, you'll do that? Okay. I am coming back for office hours, so can you tell me when these are done? Let me write this stuff up on the board and pass these out. Can you grab those and pass it along, please? This is the sample.